All right, welcome. We are doing the exam that I gave my class last semester, just for some practice. So notice that I put some some like symbols, useful like symbols and stuff like that. These are just like formulas and equations that you can have. I'm not like giving you the context for what these things mean. I don't like to do like equations sheets and stuff like that, just because I don't want to have to like check them for like all like 70 of my students or whatever. I have 2 sections. So I just like to give you guys like all like a set like collection of things that you can use here. Okay. These right here are like or actually everything up here. These are just the substitutions from that one section on substitutions. And then here, this is just your integrating factor. So this first question, I should have written it differently. I should have said specifically to use the method of substitution to do this problem, or just made the problem like harder in a way that you could only solve it using substitution. But as written, like there's no reason that like you can't just like look at this and just be like, oh, this is an exact differential equation. Because if I do del y of this first one, I get 1. If I do del x of the second term, I also get 1. So it's exact, so you could just solve it just using the method that we do with exact differential equations. So that was my bad. I didn't like, obviously if someone noticed that, I had no choice but to mark it correct. If you can outsmart me in my writing the exam, then like you deserve the points, obviously. Yeah, so I learned my lesson though. So future problems like this would probably say, like specify you must use the method of substitution to do this problem, or I would like write it in a way that like it's not exact, it's not linear, it's not separable. Like you have to do a substitution on it. So anyway, let's just do the substitution and see what we get. And for the record, if you were to do this using like the method that we use for exact differential equations, the solution that you get will look a little bit different than the solution that we're going to get right now. I had to actually like restart this video because I was getting different looking things, but I just had to play with it for a while to convince myself that I was actually getting the same like equivalent answers for both of them. So you could do u is equal to y over x. You might also be able to, you're probably also able to do v equals x over y. Just either one of these two substitutions up here is going to be valid. It's not like a Bernoulli's equation, so you're not going to have to do this guy. And it's not one of those ones where it's like y prime is equal to like some function of ax plus by plus c, something like that. That's when you would do this one. So we'll do u equals y over x, which tells us y is equal to u times x. We compute the differential dy using a product rule. So derivative of u, or differential of u, is just du. So we get x du plus u times the differential of x, u dx. We substitute all this information into this differential equation. X plus y, which is now ux. Keep the dx there. Keep the x, and then change y to x du plus u dx equals 0. I'll group all my dx terms together. So this right now is like x squared du plus ux dx. And so if I group this in here, I'll have 2 ux's, right? So I'm just going to make this a 2ux, and then plus x squared du. And I'm just going to go ahead and subtract that x squared du to the left-hand side. Equals negative, okay? So just bringing that over to the right-hand side. I forgot my equals 0 over here. And now I can also modify this guy here by factoring out an x. So I'll factor an x from that. I get 1 plus 2u. And now I can just separate my x's and u's. So I'll divide this x squared over, and I'll divide the 1 plus 2u over. So dividing x squared, x over x squared is just 1 over x. And on the right, I'll keep that negative there, negative 1 over 1 plus 2u du. I can now integrate both sides. Ln of absolute value of x on the left, and then this would be negative 1/2 ln of absolute value 1 plus 2u. I'll put the plus c over here. We need a plus c somewhere. Probably doesn't matter where. Maybe I'm going to try I did the plus c on the left side last time. I'm going to put it on the right side, see if it works out any better. All right. Notice that I had to include this like 1/2 right here, just because if I do the derivative of ln of 1 plus 2u, I would get 1 over 1 plus 2u times, by the chain rule, the derivative of 1 plus 2u, which is a 2. And that 2, I need to divide by 2 to cancel that 2. All right. You could also do this integral just using like another substitution, like set w equal to 1 plus 2u, and then dw would be 2 du, divide through by a 2. That would be, excuse me, that'd be where that half comes from. Anyway, enough of that. Let's see, what should I do? Okay, I'm going to do e to the power of both sides, because I don't want to deal with these ln's. So I get e to the ln of absolute value of x, which is x, I don't know why it's blue, equals e to the ln. I'm going to bring this negative 1/2 as an exponent for this. 1 plus 2u to the negative 1/2. And then this is like times e to the c, just using exponent rules. E to the this plus this is equal to e to the this times e to the that, and then I'm going to just replace e to the c with just like a different c. So c times absolute value 1 plus 2u to the negative 1/2. Absolute value, and I can drop the absolute values here too, because I just have a c in front, and that c can account for like the plus or minus. Okay. Parentheses are looking a little too similar to the c. I'll drop the absolute value on the x as well. Okay. All right, I'm gonna divide through by c. Yeah, I should have put the c on the left. Oh well. Doesn't really matter. And then I don't... Okay, so now I'm going to sub back in for y. U is equal to y over x. So this is 1 plus 2y over x to the negative 1/2. Goes 1 over c times x. See, is it asking for an explicit solution? Okay, it doesn't really specify if we should find an explicit or implicit. I'm also going to do a better job of making it clear which one I want here. This is a perfectly fine implicit solution. If you wanted to find an explicit solution, I'll go the extra mile right here. If you don't care, you can just skip ahead and just avoid watching me struggle. Okay, so I'm going to raise both sides to the power of -2 to cancel out that negative 1/2, because exponents multiply. By the way, 1 over c is just going to be another constant, so I could just call that c. Actually, let me do it this way. I'll just distribute the -2 to both this and the x. And on the right side, I just get 1 plus 2y over x. Yeah. Okay. I'll multiply, or I'll subtract this 1 over. So we get minus 1 plus 2y over x. And then 1 over c to the negative 2 is the same as just like c squared, but constant squared is just a constant. So this right here is just going to be a constant, and I'll just keep this x to the negative 2 here. And then I will multiply through by x. So cx to the negative 1 minus x is equal to 2y. And so y is equal to, just dividing through by a 2, cx to the negative 1 minus x. Okay. Sorry, minus like 1/2 x. I just had to pause just because I wanted to check my work on this, just because there's a lot of steps here, and just trying to be careful that I did everything right. All right, slope field, dy dx is equal to x over y. Then use your slope field to sketch a particular solution to the IVP dy dx equals x over y, and y of 0 is equal to 1. There might have... wait. Okay. Yeah, this is fine. Okay. So let's sketch the slope field first. So dy dx is equal to x over y. We have to go to like each point on this grid and just put like a little line segment corresponding to whatever slope we have at that point. So at like 0, 1, this point right here, x is 0, y is 1. So what would our slope be? It would be 0 over 1. So that's our slope would just be 0, right? So we'll put like a line segment with slope 0 right there. And you can imagine like 0, 2, the slope there would also be 0. Slope, I should probably use a different color. Let's use like blue or something. So anywhere on the y-axis, the slope is going to be 0, except for at the origin, because at the origin you have 0 over 0, which would be undefined, so we won't put anything there. At 1, 1, the slope would be like, here we're at 1, 1, slope would just be 1 over 1, which is equal to 1. Over here, we're at like 2, 2, so the slope would be 2 over 2, which is equal to 1. Get rid of that, get rid of that, get rid of that. Same thing over here, slope is going to be 1. Down here, slope is 1, slope is 1, slope is 1. But over here, this is like 1, 2. Slope is going to be 1 over 2, so the slope would just be 1/2. So be a little bit flatter. And then up here, the slope would be 1/3, so even flatter still. Over here, the slope would be 2/3. Here, okay, what about this point here? Here, we're at 2, 1, so the slope would be 2 over 1. So slope is just 2, so it's like steeper there. So I'll put like a pretty steep slope at that point. So something like that. Over at this point, this is 3, 1, so the slope will be 3 over 1, so that'll be very steep. Over here is going to be like 3 over 2, so it's like pretty steep, kind of steep. And then you can just kind of keep going from here. So over here, slope is going to be like negative 3 over 3, negative 2 over 2, negative 1 over 1. Those all just cancel out to just negative 1. Same thing with like down here. Boop, boop, boop. What about this point here? We're at 1, negative 2, so our slope will be 1 over -2, so -1/2. So it's going downwards and it's like kind of flat. Over here, it's going to be like a -1 over -2, so +1/2. So it's like flat but going upwards. Over here, it's going to be 2/1, -2/1. Or, yeah, 2 over -1 equal to -2. Here, it's going to just be +2, because we'll get like a double negative, cancels out. And then maybe at this point you can kind of see like a pattern developing, so I'm just gonna kind of fill in that pattern as we go. Here's like -3, here's like -3/2, +3, this is -3, this one is -2, this one is like -1/2, -1/3, this one is just -3. Okay, so anyway, that's our slope field. Notice that I didn't do anything on the x-axis, so you could kind of make sense of this. So like 1 over 0, you can kind of interpret that to have a slope of like infinity, so it's just a vertical line, but then it would just like be super undefined at 0, 0. We won't really worry too much about that. And let's now use this to sketch a solution to the IVP y of 0 = 1. So we're at the point x = 0, y = 1. So x = 0, y = 1, we're right here. So we have to go through this point on the graph. And the slope field kind of tells us how to draw our solution curve. So it has to be like kind of flat over here and then just sort of flowing along the slope field. So it should sort of do something like this. So you can kind of see that everything is like flowing into these like this x over here, sort of flowing into that. Like these are sort of like asymptotes for the solution curve. If I were to start like right over here, it would do something like this. Yeah, something like that. If I were to start right here, it would do something like this. If you were to include these like vertical lines, it would do something like that. Just go off like that. Anyway, this like red curve right here, this would be our solution. Oops, I forgot to delete that from earlier, but whatever. Okay, so we have this IVP, x dy dx plus 2y = 3, y of 1 = 2.5. We need to find an explicit solution to the IVP. Okay, I did mention explicit here. So we have to solve for y. So first thing that you want to do is normalize this equation just by dividing by x. That's what that line that I deleted from earlier is, so I'll just put that back. And then we just use our integrating factor method. Remember, I'm giving you the formula for the integrating factor on the front page if you can't remember it. So our integrating factor is mu of x equals e to the integral of whatever p of x is. What is p of x? Well, once you normalize, it's going to be whatever is attached to the y. So it's going to be 2 over x here. Note that this is positive 2 over x. If this was like minus 2 over x, then you would put a negative over here in the integral. So the integral of 2 over x is 2 ln of absolute value x. So this is e to the ln of absolute value of x squared, which is just equal to x squared. And I can drop the absolute values just because x squared is always positive. Multiply both sides by my integrating factor. I get x squared y prime plus 2x squared over x is just 2x times y, and then is equal to 3 over x times x squared, simplifies to 3x. The left-hand side should hopefully be equal to the derivative of x squared y, and we should always check this. So if I do a product rule in x squared y, I get 2x y plus x squared times y prime. So it does look like we're getting, we're reversing the product rule correctly. We just have 3x on the right-hand side, which we can then integrate both sides and get x squared y on the left, because we're just integrating the derivative, and get 3 over 2x squared plus a constant c on the right. So then y will be 3/2 x squared plus c all divided by x squared. So just dividing everything by x squared. 3/2 x squared divided by x squared is just 3/2 plus c over x squared. I can't just write like plus c over here. Otherwise, I would just get y equals 3/2 plus c. So that would be like, I mean, that would be telling you that like y is literally just like a constant function, which is definitely not what's going on here. And y of 1 is equal to 2.5. So we get 2.5 is equal to 3/2. 3/2 is 1.5. Might as well write that out. Plus c over 1 squared. 1 squared is just 1. So I'll subtract 1.5, and I get 1 is equal to c over 1, which is c. So that's our c value. So our solution would be y equals 3/2 plus 1 over x squared, 1 being our c value. What's our largest possible interval of existence? So I go up here to my differential equation and I look at places where p of x and f of x are discontinuous, and they are discontinuous at x equals 0, so we have to throw that out. Our IVP says y of 1 equals 2.5, so we need to be able to plug in x equals 1 into our function. So our interval has to include x equals 1, and it can't include x equals 0, so we have to do 0 to infinity. All right, let's verify that our solution satisfies the original differential equation. So here's our solution. So I'll just copy that over. I'm going to write that as x to the negative 2 so I can take derivatives. Let's just go right ahead and take the derivative. Negative 2 x to the negative 3 would be our derivative. What is our differential equation? It's that. Notice that I'm just saying verifies the differential equation, not necessarily satisfies the IVP, although I could certainly say that just so you can double check that, like, if you plug in x equals 1, that you do actually get out a 1.5, which is a good thing to, be in the habit of checking. But I only have so many things I could ask you on an exam. So what's our left-hand side? X times dy dx, which is negative 2 x to the negative 3, plus 2 times y. Y is 3/2 plus x to the negative 2. So this left term would be negative 2 x to the negative 2. And then distribute this 2 to both the terms, and I would get 2 times 3/2 is 3, plus 2 x to the negative 2. What do you know? This term and this term are just going to cancel out. We're left with 3, which happens to be our right-hand side. Okay. Use Euler's method with step size h equals 0.1 to approximate the value of y of 2.3. Given this information, y prime equals 2x minus y, and y of 2 is equal to 1. I feel like I probably didn't need to give you like the whole table. I feel like the table sort of like handholds you through the problem, so I'm not sure if I would give you the table, the whole table again, but or if I did give you the table, if I would just like remove the information at the top, just so you can sort of organize your work or whatever. I don't know, I haven't decided. But you should know how to do this problem with or without the table is what I'm saying. So anyway, I'll do it with the table, because if I didn't have the table, I would just write my own table. The point that we start with is going to be 2, 1. This just comes from this IVP right here, y of 2 equals 1. And then our whole process is going to be, all right, figure out the slope, and then add previous y value plus slope times your step size, and that'll give you your next y value. So what's our slope going to be? It's f of 2 comma 1. So it's 2 times 2, which is 4, minus 1. So slope is 3. Okay. So new y value, y sub 1, is equal to previous y value of 1 plus slope times step size. Step size is 0.1. So this is like 1 plus 0.3, so just 1.3. So new y value is 1.3. New x value always moves up by whatever our step size is, which is 0.1. So x value is going to go up to 2.1. What's our slope going to be? It's f of 2.1 comma 1.3. So this is 2 times the x value, which is 4.2, minus the y value, which is 1.3. This is equal to 2.9. Is that look right? 42, 13, 29. Yeah, I think that's right. Okay, so y sub 2 is going to be previous y value, 1.3, plus slope times step size, 0.1. So this is 1.3 plus 0.29. Remember, multiplying by 0.1 just moves the decimal over, so we can just do this. So this would be 1.59. So the next x value just goes up by 0.1, and new y value is 1.59. And looks like after this point, it's going to get a little complicated. So get your mental math ready. All right, so we do 2 times the x value, which is 4.4, minus the y value, 1.59. So I'm going to subtract those. C is to carry that. So 10 minus 9 is 1. 3, carry that. It's an 8. 2.81. Okay, so 2.81, if you remember how to do subtraction, you could use a calculator, I don't care. Y3 is previous y value, 1.59, plus slope, 2.81, times step size, 0.1. So 1.59 plus 0.281. Just move that there. Put a 0. 7, 8, 1.871. Okay, so this would be our final answer. And we know not to go any further than this, because if we were to put the next point in the table, it would just be like 2.3, 1.871. So it would be telling us, oh, the y value, according to x equals 2.3, would be 1.871. So y of 2.3 is equal to 1.871. So you don't have to do any further work here. So 1.871 would be the final answer. Cool. All right, here's an exact equation. So I start off by just telling you to show that the differential equation is exact. So let's do that. So we'll do... So this first term has a dx in front of it, which tells us we need to take the derivative with respect to y. 3x squared times y, that derivative is just 3x squared. Derivative of e to the y with respect to y is just e to the y. And then del x of the other thing, x cubed plus x e to the y minus 2y. Derivative of x cubed is 3x squared. Derivative of x times a constant is the constant, which is just e to the y, and the derivative of negative 2y is 0. So get the same thing, so it's good. Find an implicit solution to the initial value problem. All right, this is where you want to find your parent function, f of xy, which is just going to be, you could integrate either of these two things. I always just do this one first, so I'll just do the second one just to be different. X cubed plus x e to the y minus 2y dy. So integrate that. X cubed is a constant, so x cubed integrated with respect to y is just x cubed times y. X e to the y, x is a constant, so constant times e to the y integrates to just constant e to the y. And then integral of negative 2y is negative y squared. And then this is plus like a constant, which is like a constant with respect to y, so it could have x's in it. So g of x. Now del f del x, if I take the derivative of this whole thing, that should equal what I get over here, 3x squared y plus e to the y. So what's the derivative of this? Well, I get 3x squared times y plus derivative of that is just e to the y. Derivative of that is just 0, and plus g prime of x. And that's equal to 3x squared y plus e to the y. Oh, it looks like everything just cancels out here. So I guess that's nice. So that tells us g prime of x is equal to 0. So g of x itself is equal to 0. All right. So this right here is our parent function, and our solution is just going to be, all right, so left-hand side of this is the derivative of parent function, and the right-hand side is 0. So if I have derivative of f on the left equals 0 on the right, I can integrate the left and the right, and I get that f is just equal to c, right? So I'll get f, my parent function, is equal to constant c. And then y of 1 is equal to 0. So I plug in x equals 1 and y equals 0, figure out what my c is. So I get 1 cubed times 0 plus 1 times e to the 0 minus 0 squared is equal to c. So most of this is equal to 0 except for e to the 0, which is 1. So c is equal to 1. So x cubed y plus x e to the y minus y squared is equal to c, which is 1, would be our solution. All right, what about this extra credit question down here? Verify using implicit differentiation that your implicit solution satisfies the original differential equation. What that means is we have to take this guy and, wish I didn't highlight it, oh well. We have to take that and just do implicit differentiation on this. So implicit differentiation looks like the following. So if I do implicit differentiation on x cubed y, I would get 3x squared dx plus x cubed times the derivative of y, or differential of y, which is just dy. You could like have like a dy dx over here and then not have a dx over here. They're doing the same thing. One of them's a differential, one of them's a derivative. It's all the same. Okay. Next term, x e to the y, differential of x is just dx, so I'll do e to the y dx, plus x times, derivative of e to the y is just e to the y times the derivative of y, so e to the y dy. Have to do a chain rule there. And then minus y squared, I'll do minus 2y times dy. And on the right-hand side, derivative is just 0. I now group all of my dx terms together and all of my dy terms together. So I get dx term, I get 3x squared plus e to the y dx. And then dy terms, I get x cubed plus x e to the y minus 2y dy. And what is our original differential equation? It's 3x squared plus e to the y dx, and x cubed plus x e to the y minus 2y dy, and equals 0. So yeah, that's it. I was kind of nitpicky last semester when I was grading this. Some people just showed that the left-hand side is the differential of the function f, which is a good way to check your work, but it's not the same as like doing implicit differentiation on an equation. And so I kind of nitpicked that and given that. Basically what I'm saying is use implicit differentiation to verify a solution as opposed to checking your work. Those are different things, even though the work for them looks pretty similar. Okay. Anyway, that's it for that. I'm gonna pause this video. I'm gonna go to the other practice exam. All right, so most of the questions on the practice exam were pretty similar to the problems that showed up on the actual exam. So just for the sake of like not getting too repetitive, I'll post the solutions to this, but I'm not gonna do a video for like the whole practice exam. That's fine. So I'll just do this problem because it's like different enough to warrant its own video. So consider this differential equation: y squared minus y minus 6 is equal to dy dx. Let's find our equilibrium solutions. By the way, finding critical points and finding equilibrium solutions, it's pretty much the same thing, although your final answers are slightly different. Critical points are like y values, whereas equilibrium solutions are functions, like y of x equals 2 or something. Okay, so if I factor this would be y minus 3 times y plus 2. And if I were to set that equal to 0, then that would tell me that y is equal to 3 or negative 2. So our critical points are y equals 3 and negative 2. So our equilibrium solutions are like y or y of x equals 3 and y or y of x equals negative 2. Those would be our solutions. Classify all critical points as stable, unstable, or semi-stable. So really, we just want to like draw a phase line diagram. Okay, so 3 and negative 2. So put negative 2 here. I'll put 3 up here. And then I just need to figure out if our derivative is increasing or decreasing on each of these 3 intervals. So if y is bigger than 3, so y prime is equal to y minus 3 times y plus 2, right? So if y is bigger than 3, then is y prime going to be positive, negative, or what? So if I plug in like 4 into this, I would get 4 minus 3 times 4 plus 2. That's going to be 1 times 8. So it's going to be positive, right? Oops. It's going to be positive. So I'll put an up arrow there. If y is between negative 2 and 3, so I could like plug in 0, I get like negative 3 times positive 2, that would be negative. So I get something negative. And if y is less than negative 2, y prime would be, so if I plug in like negative 3, I get like negative 6 times like negative 1. So negative times a negative is a positive. So we get positive, it's going up. So boom. So so here, these two are both pointing into the critical point, and these two are both pointing out of the critical point. So this one right here would be unstable because they're both pointing like away, and this one right here would be stable because they're both pointing inwards. If you were to get a situation where, like for example, let's say that like this one right here was actually like pointing down, so they're like both pointing down, that would be semi-stable. But it's not, so I'm going to get rid of all that. Okay. Use your above work to sketch a graph of the 3 particular solutions corresponding to each of the initial conditions shown here. Okay, so this is basically just taking this phase line diagram and expanding it out to drawing your solutions. So here's our y-axis. Here is our x-axis. So this is like y equals 0. Oh, sorry, x equals 0. This is the x-axis given by y value is equal to 0. And let's see, here is 1, 2, 3, negative 2. So put a little dotted line over here at negative 2, and then a dotted line at positive 3. So here's 3, here's negative 2. And these correspond to our equilibrium solutions. So this right here and this right here, these are your equilibrium solutions, right? Now, what about the solution y of 0 equals 0? So that would mean the solution has to go through the point 0, comma 0. Okay, well, on this interval, this arrow is pointing downwards. So if it's pointing downwards, it's going to look like this. If it's pointing upwards, it has to look like this. So it's pointing down, so it has to look like this, and it has to go through 0, 0. And it has to like always be decreasing. So the slope is always negative, except it has to like level out. Like it can't crash through the equilibrium solution, right? Because the slope is 0 at the equilibrium solution. So it looks like that. Up here, y prime is positive, so slope is always positive. So always has to be doing something like that. So here's 4. So it's going to look something like this. Something like that. If it was negative, then it would look something like that. Down here, if it's negative, it looks like that. If it's positive, it's going to look like that. This is positive, so it's going to look like that. What was it? Y of 0 equals negative 4. Here's negative 3. Here is negative 4, so it has to cross through there. Good enough. So it looks something like that, right? Boom. So this slope, note that the slope is always positive, which corresponds to this phase line diagram saying the slope is positive, which came from this work over here, which said that if your y value is negative 2, like here our y value is negative 4, then your slope has to be positive. So the graph is going upwards, it's sloping upwards. All right, so these would be your 3 particular solutions corresponding to each of these 3 initial conditions. All right, I'm gonna end the video here. Note that this is not like a comprehensive like study guide or anything like that. This is just like a collection of problems to help you kind of gauge your understanding with everything. The exam is not going to be exactly like this collection of problems. It will probably be like fairly similar with some differences here and there, obviously. As I'm, continually tweaking things. I'm going to end the video here and then go finish writing up the solutions for this practice exam, and then I'll post them and then post the video sometime this weekend. Have a great day and happy studying.